Hi everyone. So in this lecture, well, not lecture, examples, we're going to talk about surface area. You probably just finished watching, maybe not just finished, but you just finished working on length of curves. And now basically, the way I like to think about this is, you have this formula, right, for the length of a curve. You could find the length of this curve. And now we're going to rotate it, let's say, across the x-axis and get... oh, that didn't work out, did it? That's not its reflection. Something like this. Okay, and we want to just find the surface area of this. And so you found a formula for it. They gave you the formula. And well, I think it's good, of course, to know these formulas. And I'll probably give you some of these formulas on the test. I also think it's important to understand why this formula works. So what does this give you, right? This gives you the length of the curve. That's what this kind of square root of 1 plus square root of f prime of x squared is. And then what this just gives you is, if you look at taking a little slice of this and rotating it around, that's just the circumference. This right here is just the circumference of that circle right there. So this is like your circumference. So you're basically taking this length, right, and you're just swooshing it all around. And that gives you kind of the distance that this length travels through. That's kind of how I think of the area. I know it's much more complicated than that, and you read through the derivation of all of this and why it works. I'm sure it was a thrilling read, but that's kind of what you want to think about, is just I'm taking this length and then I'm just swooshing it around, right? And what is the total distance that this length traveled? Well, it was the circumference, which is 2 pi f of x. So this example, it's gonna be a pretty short little video also, kind of like the arc length. And let's do this. So my first example, we have the graph of y equals x cubed over 9 on the interval 0 to 2. I'm just going to make my own axis here. I know usually I use the ruler and stuff, but I think we'll be right if I just do this. Man, maybe not. That was a horrible x-axis there. So between 0 and 2, if I think about what the graph of this looks like between 0 and 2, right? Well, nope. Let's see. So 0 is 0. If I put in 1, I get 1/9, right? So pretty little here. If I put in 2, I get 8/9. So almost 1. I should have given myself a little bit different, but this is a cubic, right? And we're just looking at interval from 0 to 2. Normally the cubic is going to go something like this, but I just want between 0 and 2. And then I'm going to rotate that about the x-axis, and we're going to get some surface, right, like this, and I just want the area of that surface. So not a whole lot to draw with these, especially because we're kind of just given the kind of the formula for it. But one thing to realize is I rotated about the x-axis, so I will be integrating with respect to x. So unlike, remember, shells are the only thing that switches whatever axis you rotate about. It's the opposite variable of integration, right? But everything else in this section and in these revolution stuff is you integrate with respect to whatever the axis is that you're rotating about, or any axis that is parallel to that. Okay, so let's just do it. So my area then, right, is going to be the integral from 0 to 2 of 2 pi times my function, which is x cubed over 9, times the square root of, this is, remember, the arc length of this section right here, 1 plus the derivative squared. Now, you might do some, down here we might have, and I probably should have done that, we might have, taken the derivative. So this is 3x squared over 9, or x squared over 3. And then, even if it's a little more complicated, you saw that in the video with the arc length, sometimes we might want to even spend a little bit more time kind of figuring out what we have, because we might have some, who knows, we might have some fun algebra we get to do. So I'm going to square this, and I'm going to get x to the 4th over 9. And I am just going to pull out some of my constants here. So I have that 2 pi over 9 I can pull out. I'm integrating from 0 to 2. I have this x cubed, and now I have the square root of 1 plus x to the 4th over 9. And actually, what's nice about the surface area formula, unlike the arc length formula, is because you have this f of x right out here, it kind of gives us a little bit more opportunity to do different examples, because I can do substitution. It just makes that integrand easier for right now until we kind of figure out more integration techniques. I see that the derivative of the inside is basically the derivative, it's sitting out there, we're just off by a constant. So I'm going to let u equal the whole inside. Don't let it equal just x to the 4th over 9. Let u equal the whole inside. Then what is du? Du is 4x cubed over 9 dx. But what do I want to get rid of? So this whole thing here, right, is replaced with u. What else do I need to get rid of? X cubed dx. So I'm just going to multiply by 9/4. So what is x cubed dx going to be replaced with? That's going to be replaced with 9/4 du. Okay, I want to see this work for right now. I mean, I guess if you could see what you're off by, that's fine, but so this is all kind of my side work. Now this equals sign down here, I'm dropping down. I still have that 2 pi over 9, the integral from, I'm not going to go from 0 to 2. I have to change my bounds. But what am I going to have? I'm going to have a 9/4. Oh, that's pretty nice. There's a reason that happened. Times u to the 1/2 du. Everyone see what we did there? Well, you can't answer me. So I'm going to assume, remember, this is all kind of my inside work here. Have to change my bounds, people. You have to change your bounds. When x is 0, right, I have this relationship between u and x. If x is 0, I get 1 plus 0, then u is 1. So I know that this is 1. When x is 2, right, then I'm going to have 2 to the 4th is 16, so 16 ninths plus 1, I think that's 25 ninths. Oh, I hope that's right. Is that right? I'm talking to myself. That doesn't probably bode well for, you know, me. I think so. 16 plus 9 is 25, right? So if I get a common denominator, that's 25 ninths. Those are both perfect squares, so I bet that's right. All right, change your bounds. Change your bounds, people. I'm picky about notation. If we put an equal sign, it best be equal. It had better be equal. And I want you to use equal signs. Sometimes my students will be like, well, then I'm just not going to put equal signs. No, you need to put equal signs. Simplify a little bit. The antiderivative of u to the 1/2 is u to the 3/2 times 2/3, right? And I evaluate from 1 to 25 ninths. And now I don't have to go back to x's because I changed my bounds. That's the beauty of it. So let's kind of go through this together a little bit because I know sometimes this can be the hard stuff. So let's put 25 ninths to the 3/2 minus 1 to the 3/2. So 25 ninths to the 3/2. Square root of 25 ninths, right, is 5/3. Okay, and then I'm going to cube that. That's what that means. So I have 125, that's 5 cubed, all over 27, right? 3 cubed. And then 1 to the 3/2 is just 1, but I'm going to have minus 27/27 because I see I have a common denominator, right? Or I want to get a common denominator. So that looks like it's pi over 3 times, oh man, I hope this is right, 98/27, I think. And I don't believe 98 is divisible by 3. So it looks like we get 98 pi over 81. Sure. I think so. That, I don't know if that's right, but that's probably right. Anyway, I could have messed up on my arithmetic. That has happened to me before. It's embarrassing, but it's true. Happens to everybody. But that's kind of our process for doing the surface area. Not too hard. Let's do one more quick example, and then you know what? I think we'll call her a day because that was a good time, and this isn't too bad of a section. So the last example here, we'll do this in terms of y just because it's kind of fun. So we have the graph of x equals 1 minus y on the interval 0 to 1. Realize that interval is in terms of y, that's 0 to 1. It's actually going to be the same in x too, but because y is the dependent variable, or excuse me, independent variable, and x is the dependent variable, that 0 to 1 implies that's y. We're going to revolve it about the y-axis. We are not doing shells, we're not doing volumes, so we know that the y-axis means we're going to be integrating with respect to y, right? Okay, sorry about that. What is the area of the surface generated? So I'm just going to draw a quick little picture. I don't think this is going to, help us really one way or the other because it doesn't really matter, but I mean, it matters. I shouldn't say it doesn't matter. But let's just kind of see what happens. So from 0 to 1. So when y is 0, x is 1. So when y is 0, meaning I've gone nowhere up and down, x is 1. So I know I'm here. Let's do a different color. When y is 1, right, x is 1 minus 1, which is 0. So when y is 1, x is 0. So it looks like this is going to be what I have. I have just a line. That makes sense. And I'm rotating it about the y-axis, right? So about the y-axis. And so I get a cone. So whatever we get here, we should be able to check with, it's called the lateral surface area, meaning it doesn't include the surface area of the bottom of the cone. It's just the cone itself. And I'll let you check that on your own. So remember, our surface area, right, is going to be given by, you know, c to d now because it's in terms of y, 2 pi g of y times the square root of 1 plus g primed of y quantity squared. This should be pretty easy. dy. Again, this is the length, right, of the curve, and this is the circumference of the revolution. All right, so what's my area then? I can take those little lengths, right, and then I can revolve them around the y direction. Where can I take those little lengths? I can take them from 0 to 1. 2 pi, what is my function, right? 1 minus y. And then I have the square root of 1 plus, what is the derivative of 1 minus y? With respect to y, it would be negative 1. And that's going to be squared. I want to point something out really quick. Now, this doesn't actually have to do with calculus, but it's a mistake I see all the time. This, my friends, are we friends? Let's do it, is 1. This is negative 1. In this case, the negative is squared. In this case, it's not. So those parentheses are important. Oh, whoops, I'm sorry, I keep going to, there we go. Those parentheses are important, right? Those parentheses are important because you want to square the negative with it. All right, so let's finish up. Oh, Sarah, come on. All right, almost done here. So this should be pretty easy because the derivative is just a constant, right? So this all right here is just the square root of 2. So I can bring out, I have 2 pi root 2 on the outside, 0 to 1 of 1 minus y dy. And now I'm ready to go here. So I have 2 pi. Don't forget to take the antiderivative. I see students do that sometimes, I think, because you're just doing so much to set these up that you feel like you've done everything you should. Let's plug in the 1 and the 0. You don't want to do that quite yet. Go ahead and take the antiderivative. Don't forget to do that. So I have 2 pi root 2. If I put in the 1, I get 1 minus 1/2, which is 1/2, right? If I put in the 0, I get 0. These 2's cancel, and my final answer is root 2 pi. And I bet if you look that up under your lateral surface area of a cone, that would be it, right? A cone of base radius 1. Not much else to do there, you guys. I hope that makes sense. Let me know if you have any questions, and enjoy.